Now we shall be trying to understand the very famous Ampere's Circuital law. Now what does Ampere's Circuital law states in the condition of magnetic effects of the current is that it states that the line integral of a magnetic field over a closed region is basically equal to the permeability of that medium times of the current flowing in the region. Very hard to understand? No, very simple. Let us try it with the Ampere's Circuital law states that the line integral of the magnetic field, the line integral, say for example, let us take it likewise. First of all, the line integral of the magnetic field over a closed region in a medium. This means that this integral to be in a closed region in a medium. Let us check for the time being. The medium is free space or vacuum or air. So it states that the line integral of the magnetic field over a given or a closed region, right, is equal to the permeability times of that medium. What is the permeability of free space or vacuum? Yes, it simply equals to mu naught. The permeability times of the amount of electric current in that closed region. Let us check the amount of current in this closed region is equals to I. So this is simply the Ampere's Circuital law, where it states that the closed integration of VdL is equals to mu naught I over here. Now what if that, say for example, this GL, as we can see it as a vector and B as a vector. Now what if there is a certain angle between B and D? Say for example, the theta is the angle between B and D, then it may be represented like integration of over this closed loop BdL cos theta is equals to mu naught I. Why have we taken cos theta? Because over here, see that BdL, over here this is a dot product, but simply this is actually not treated as a dot product. This is seem to be a dot product, but actually if we want to understand that this will be something like this, because it states that the line integral of the magnetic field over a closed region in a medium is equal to the permeability times of that medium of the current flowing through in that region, right? Now this is the Ampere's Circuital law, and we should try to understand that what is the proof for this, taking the help of a practical application. Now let us check, for example, over here we take that this is, say for example, a straight wire, an infinitely long straight wire carrying current. So the current will be, let us say for example, in this direction. If the current is in this direction, this is a straight long wire, and we wish to find out the B at, say, a point at this region, at this point. What is the amount of B? Say for example we draw a circle such that this point lies on the circle, then obviously this will be the radius, say for example small r, of this circle. Now if the amount of current is flowing over here is I, we know that the B will be tangential to this circle which is formed at any point. The B will be tangential to the circle, right? So this is the B. Now if we take this is the point, actually the point was taken over here. Say for example this point as P, this small point, and if we see it, we will see that that is actually a small length, a dl, right? And the direction of the dl, we shall be finding it in the same direction of B, right? Now over here what we can do is that this red area mark, let us take it as a closed area, okay? And we apply this Ampere's circuital law. Let us say, for example, in this circumstance, we take the integration over the closed loop of B dl cos theta. It will simply be equals to integration over the closed loop of B dl. Over here, theta is the angle between this L and B, right? As we have seen over here, this GL and B. This is GL and this is B. They are actually along the same line. So what will be their angle between them? Simply equals to 0. And the value of cos 0 is simply equals to 1. So this will simply be, this expression will be looking like integration over the closed interval of B dl, right? So we can write it as equals to B, or say for example, let us write it as integration. As we have studied for the infinitely long wire, what will be the B at a point which is actually R meters away. So we know that the magnitude of this B was actually equals to mu naught I divided by 2 pi r when it is separated by a distance of r, right? And now let us put the value of this B over here. It is mu naught I divided by 2 pi r multiplied by dl, right? This thing being a constant, it shall come outside, so this expression will look like mu naught I divided by 2 pi r, the closed loop integration of dl. Now what is the closed loop integration of dl? See over here, the dl is this part. Again this will be some dl over this part, this will be the dl over this part, but the entire thing will lie along on this circle. So the integration of all the dl's on this circle will actually mean as the perimeter of this circle, and as the perimeter of this circle with the radius being equals to small r, this will be simply equals to integration of dl as 2 pi r, right? So we can write this as equals to mu naught I divided by 2 pi r multiplied by 2 pi r. Now look over here. This 2 pi r and this 2 pi r on the denominator and the numerator will cancel out each other, leaving that over here this term we can write at this. So the integration over this closed loop BDL will be equals to mu naught I. Now this is the actual thing which we have looked in the Ampere's circuital law. So now we can understand that how we could apply the, say for example, this Ampere's circuital law in order to find out the value of B, right? Thank you.